All right, we'll get started then. So today we just have some conceptual topics to cover regarding hypothesis testing and statistical inference. Also a little bit on sampling. So we'll cover that, and then I'll just do kind of a very brief recap of stuff covered in the course. For this week, really your homework will be to go over the practice final exam. There's a practice final exam posted under week 10, and so your homework this week is to work through that, and then next week for review we'll go through all of the answers on the practice final and get anything straightened out if there's still any questions. Yes, question. Yes, there will be a quiz next week. It'll be just covering the conceptual stuff from today. There's a few. There's also a practice quiz posted online as well. Okay. I'll also do some grade calculations for you guys next week, so you guys will know exactly what you need to get on the final exam. For whatever grade it is that you're looking for, okay? So, for some of you that's passing, or for some of you that means you want to get an A. Depending on who you are, it'll have it broken down and say, this is what you need. And I'll talk more about that next week. Okay, so I want to just cover a few topics on sampling, okay? And I think there's, one section in the textbook, I believe it's chapter 12, that covers some stuff on sampling. But really I'll just kind of go through them briefly here, and really you're just responsible for the stuff I put in my notes here, okay? Sampling methods, okay? So far, all of our statistical inference is kind of based on the idea of that we have a simple random sample, okay? So we've covered really two statistical inference methods, being confidence intervals and hypothesis tests, and those assume that our samples were selected via simple random sampling. And so simple random sampling, we've already spoken about this, but it's worth just writing about again. Simple random sampling begins with a sampling frame. Okay, and the sampling frame is ideally a list of every single person in the population. Okay, and to get a true sampling frame is actually quite difficult. unless you're dealing with you know, a single organization like a company or a school. Okay. Otherwise, getting a true sampling frame for, you know, something a bit more complex, like the city of Los Angeles, very difficult to do. Okay, but once you have your sampling frame, you will use a random device. Such as, you know, a computer, random number generator on a computer, or, you know, a way to, you know, ping pong balls or whatever it might be. You will use a random device to select individuals from the sampling frame one at a time. Individuals one at a time from the sampling frame. At random. Okay, and then the key here is that every individual has an equal chance of being selected. And then every possible sample has an equal chance of being selected too. Okay. There are other sampling methods as well. And so, you know, they're worth mentioning and covering. Okay. So we have stratified, or here, let me start off with systematic sampling. In systematic sampling, this works best if you have some kind of line or queue. Okay. And basically you just pull off every nth person, whether that's every 10th person or every 15th person or whatever it is. Just select every nth person from the line. Okay, so you know, every 10th or every 15th person, whatever it might be. Okay. So you know, if you sometimes when you check out at the store, every now and then you get this bonus survey thing. It says like, answer this survey, tell us about your thing. Now they might print that on every single receipt, but then in some places only print it on every 5th receipt or something like that. Okay, so that would be a form of systematic sampling. Or if you know, when you call customer service, it says this call might be monitored or recorded or things like that. They might be recording every single conversation, but then as far as active monitoring, they might, just because they don't want to have someone listening on every single one, they might, the person monitoring might only listen to every 10th call coming in or something like that. Okay, so you have things like that for systematic sampling. Okay, but if you don't have some kind of system where things are kind of flowing in a nice line, then this won't work very easily. Airport security, they have quote unquote random inspections and things like that. They could make it very fair using systematic sampling, and nobody would complain about any kind of bias for the random inspections. But then you might have people trying to take advantage of that and, I don't know, stagger themselves so they're not in, if they know it's every 10th person, they might choose to try to avoid that 10th position. So that could be a problem. And a system that would work, that would be transparent and fair, is if there's like a, I don't know, 20-sided die or something, and one side is painted red, and then you roll it, and if it lands on the red side, then you get pulled aside for extra screening, and then if it lands on any other color, then you keep going through. That would be random and fair, but I think we suspect that it is not truly random, nor possibly not truly fair either. But anyway, and maybe that's not what we want. I don't know. Okay. All right. Other methods. We have stratified sampling. Okay. And with stratified sampling, this actually makes the sampling process a little bit more difficult. But so the way this works with stratified sampling is, let's say you suspect that maybe certain demographic characteristics are related to the responses that people give. If let's say you're going to survey people, and you suspect that a certain demographic. So maybe you're asking questions about I don't know, things related to gender, and you think, perhaps the gender of the respondents will influence or be related to the responses you get. And so in that case, if you did truly random sampling, it is possible that because it's random, you might get a disproportionate number of one gender versus the other, okay? And that in turn could affect the outcome of your survey results, all right? And so with stratified sampling, you say, okay, well, I know my population, is this percentage this, and this percentage this, and this percentage this. So when you select your sample, you're going to make sure your sample has the same proportion of this, same proportion of the other group, and the same proportion of the, the other groups. You're going to make sure that the sample you select has the same proportions that the population has, okay? And that way, the responses, still may or may not be truly representative of the population, but you've at least kind of accounted for the possibility that, these different subgroups could play, okay? So, stratified sampling, okay? So, the population is made up of a few subgroups called strata. Okay? And we know what percentage of the population is in each group or each strata. Okay, and we select our sample so that the sample has the same proportions of strata. So let's say the population is 50% group A, 35% group B, and 15% group C. Okay, so we select our sample so that it too ends up 50% A, 35% B, and 15% C. Okay, these will be, the group A members, these will be 50% A, also selected random A, 35% random members of B, and 15% random members of C. Okay? But we're just we're selecting our sample so that it has the same proportions as the population. So whatever that might be. All right. And then lastly, we have cluster sampling. Okay. Cluster sampling is a method to make it easier for sampling a large population. Okay. And so if we want to do simple random sampling, we would need a list of every single person in the population. And that list might be very difficult to obtain, okay? So, for SRS, we need a sampling frame. Okay, and that could be difficult. And so with cluster sampling, what we would do is the population kind of is naturally divided into subgroups, and it's easier to get a list of every single subgroup, okay? So with population is divided or consists of subgroups, okay, called clusters. And it is possible and easier to get a list of all the clusters. Okay, and then what we do is from the list of clusters, we randomly select some of the clusters, and then we perform random sampling in the clusters. Sampling or a census, okay, of the selected clusters. Okay, so I think this is best illustrated with an example. Let's say you wanted your population. You want to do a survey of every person who I don't know, goes to church or something. Okay, so wish to survey people who attend or we'll just say wish to survey people who attend religious services. Okay. Now, this population would be very difficult to get a sampling frame. Okay, so let's just limit ourselves to Los Angeles. Okay, wish to survey people who attend religious services in Los Angeles. Okay. It would be very difficult to get this list of every single person who attends religious services. On the other hand, it's much easier to get a list of all kind of, you know, places of worship, I guess. Okay, so it'd be relatively easy to get a list of all churches and temples and mosques and every single one of those. It's much easier to get a list of that. Okay, so it'd be much easier to get a list of, you know, places of worship. Okay, and so we can get a list of all of these, and so this population naturally is kind of split into these different places of worship, and then you would perform random sampling to select, I don't know, maybe 20 or 30 different places here. Okay. Random sampling to get, you know, a sample to select some of these places, and then with the selected locations, perform either a census or random sampling within the selected locations. Okay, and that would be cluster sampling. So here it's you know, it's easier to get a list of these different places, and then you can perform sampling there. Okay, or you know, let's say you wanted to get a random sample of students or something like that. So then rather than trying to hunt down every single student individually, it'd be much easier to get a list of all the schools, which is where the students would be found. And then you would randomly select some of those schools from your list of schools, and then you would perform sampling within those selected schools. Make your life a little easier. Okay. All right, so those are sampling methods. You'll see a few questions related to sampling methods on the final. I also have a few questions listed in the practice final. There's maybe like 3 or 4 of them where I just kind of describe a scenario or a method that somebody used to perform sampling, and then you just have to identify this is an example of systematic sampling, or this is an example of simple random sampling. Okay, so you'll see that in the practice final and on the final exam itself. In my opinion, those questions are easy, and so they're meant to be kind of like easy points. But you know, just make sure you at least learn the basics of this so you don't miss out on those easy points. Okay, any questions? We're good? All right. So I want to cover a little bit more stuff on hypothesis testing, this stuff about, you know, p-values and significance levels, alpha, and all of that in a little bit more detail. And so, you know, here we're going to cover, I guess we'll say, conceptual topics related to inference. Okay. All right, so let's begin with the p-value. Okay. So the p-value, our definition for the p-value is this is the probability of observing our data or something more extreme if the null hypothesis were true. Okay. So it is, you know, the key is that it's the probability of seeing your data. It's not the probability of whether the null or alternative hypothesis is true. It's the probability of seeing your data if we assume that the null hypothesis were true. Okay. Large p-values mean that even when the null hypothesis is true, so even when the null hypothesis is true, you know, our data is likely to occur from random chance. And this means we don't want to throw out that possibility, okay? Because because it is likely to occur from random chance alone, we are not ready to, or we would not doubt the null hypothesis. Okay, and a small p-value, on the other hand, So small p-values mean that, you know, our data is technically possible, okay? Possible but highly improbable to be observed if the null hypothesis were true. Okay, so here we doubt or reject the null hypothesis. Now, our decision to whether to reject or not reject, or whether we decide our p-value is large or small, depends on our choice of alpha. Okay. Okay, and so alpha is our significance value. Okay. Alpha kind of, well, I'll get into this. Okay, so alpha is our significance value. There's something called a type 1 error. Okay, so let me talk about this. So we have errors that are inherent to the process of inference. Okay. These are errors that we make not because we did anything wrong in our calculation, but errors that we could make simply because we're making a decision. We're deciding to reject or not reject the null based on incomplete data. Okay, we do not have. The whole point of statistical inference is that we want to make conclusions about the population based on just a sample. Okay, and anytime you don't have all of the information, it's possible that you make the wrong conclusion. Okay, and that's just true throughout all of life. Okay, unless you have all of the information and know what's going to happen in the future, whenever you make a decision, you might have made a mistake. Okay, and it's the same with statistical inference. Okay, we are trying to make decisions based on a sample rather than all of the data in the population. Okay. Sample of data. Rather than the population. So we are at risk of making a mistake. And there are two kinds of mistakes we can make, and we creatively named them the type 1 error and the type 2 error, okay? Well, so this was, you know, statistics, when they were coming up, realizing these errors that could be done, they didn't have names for them, and so they call them type 1 error and type 2 error, and those names have kind of stuck around. As time has gone on, we've come up with better names. So the type 1 error is also known as the false positive, okay? So type 1 error is your decision is to reject the null, okay? Your conclusion or your decision or conclusion is to reject the null. Okay? But in truth, the null was actually true and should not have been rejected. But in reality, the null hypothesis was true. And should not have been rejected. Okay, that's a type 1 error. What would the other kind of error be? The type 2 error is the false negative. Okay, in this case, our decision, your decision or conclusion is not to reject the null. Okay, you conclude, do not reject the null hypothesis. In reality, the null hypothesis is false and should have been rejected. Okay. You know, these are the errors that we can make. Ideally, when we reject the null, it's because the null should be rejected. And ideally, when we choose not to reject the null, it's because the null should not be rejected. But if we make the wrong decision, those are errors. All right, do we have all this written down? Okay. And so what we have is our alpha, our choice of alpha reflects our willingness to make a type 1 error. Okay? So in fact, alpha is equal to the probability of committing a type 1 error. Okay, the probability of committing a type 1 error is equal to alpha. So if alpha is 5%, means you will commit a type 1 error 5% of the time. Or I'll say your risk of committing a type 1 error is 5%. Okay, and so you might say, well, I don't want to commit type 1 error. Why not just use alpha 1% or alpha 0 or something like that, okay? why not just use a tiny alpha to avoid committing a type 1 error? Okay. Well, the flip side is that if you decrease alpha, to avoid type 1 error, okay, you increase the risk of committing a type 2 error. Those go hand in hand. You can't, if you reduce your type 1 error risk using the same data, you have a greater chance of committing a type 2 error, okay? And so beta is the probability of a type 2 error. Okay? So alpha goes with type 1. Alpha will be probability of type 1. Alpha is like A, and beta is like the letter B, and that goes with type 2. So the second letter of the alphabet is B, first letter of the alphabet is A. Okay, so alpha and then beta. That's actually where we get the word alphabet from, alpha and beta, kind of just stuck together. And so, so that's what we have, type 1 error and type 2 error, okay? So let me kind of put this in a little bit more of a real context so we maybe understand the implications of having a large alpha or small alpha, okay? So I said, the default value that we use as alpha is 5%, but depending on the context, you may actually want to have a bigger alpha, or you may want to have a smaller alpha, okay? So can I flip the page here? Yeah, okay. All right, so imagine criminal trial, okay? Criminal trial. All right, and so in our justice system, we always say the defendant is presumed what until proven. So we assume innocence until proven guilty, right? So in this case, when we set up our null hypothesis and alternative hypothesis, one of this will be defendant is innocent and the other one is defendant is guilty. Which one is the null? Yeah, so the null is that the defendant is innocent because we are presuming the null hypothesis to be true until the evidence points us to reject that, okay? Okay, and so in reality, if we knew the truth, it would either be the null hypothesis is true or the alternative is true. Okay, these are the only possible scenarios regarding the the charges against the defendant. Either the defendant is innocent of the charges or the defendant is guilty of the charges. Now, and I understand life is complicated and there's things of questions of intent and all of this and whatnot. But let's just simplify things and we'll say either the defendant is innocent or the defendant is guilty. Okay, and so it's it's the prosecution's job to present evidence that will convince the jury that the defendant is guilty, okay? So the prosecution, must present evidence convince the jury that the null hypothesis is wrong, and that the alternative is true. Okay? And if the prosecution does not present enough evidence, then what does the jury decide? So yeah, if the prosecution does not have enough evidence, okay, then the jury will acquit, which means they say not guilty. Okay? Notice the jury never says we, the jury, find the defendant innocent. They always say the jury always says not guilty. In the same way, we never say we accept the null. We just say we do not reject the null. Does that make sense? Okay, so this is do not reject the null. We never say we accept the null. We never say, the jury never says they find the defendant innocent. Okay? And on the other hand, if there is enough evidence, okay, then the jury will say guilty. Okay, or reject the null and accept the alternative. Okay. So ideally, okay, in our ideal scenario, ideal cases, if the reality is defendant is guilty, and then jury says guilty. Okay? And or the reality is that the defendant is innocent, then jury says not guilty. Okay, those are the ideal scenarios. Okay? That's what we want, okay? Or, you know, if a judge, if it's a bench trial or something like that, okay? But because we never always have all of the data or never have all the evidence and we don't know exactly what happened, we are subject to making mistakes, okay? And so what are the errors that could be made? Okay, we have a type 1 error. What is a type 1 error? The false positive, which means we rejected the null when the null is true. And type 2 is the false negative, where we did not reject the null when the null was false. Okay, so what is a type 1 error in this case?
Guilty when you're innocent.
So the jury says what, and the defendant is what? In reality, the defendant is what?
Innocent.
Yeah, in reality, the defendant is innocent, but the jury says guilty, right? So that's a type 1 error. And then on the other hand, we have a type 2 error, which would be what? In reality, the defendant is guilty, but the jury says not guilty, right? The jury acquits. Okay. Now we don't want to make either type of error, okay? We want to avoid both of these. We want to avoid type 1 and we want to avoid type 2, okay? But if you had to choose which error is worse than the other, which one you would want to avoid more, which one would we say is worse? The type 1 error, right? I mean, this is always up for a little bit of debate, but you know, at least the way our justice system is set up, and I think this is the right decision, is that the type 1 error is worse, okay? So we would say type 1 error is worse, okay? Now, but of course, you know, both of these would be, either error would be a failure of the justice system. That's the truth, okay? And so sometimes, you know, we can probably think of some high-profile cases that are televised and, you know, maybe as viewers not in the courtroom, you know, we feel like, oh, for sure, this person committed the crime or something, but then, you know, the jury perhaps acquits or things like that, and, you know, maybe we feel upset. But the truth is if you can't have a system that minimizes both type 1 and type 2 errors, okay? It's not possible to minimize both unless you have all of the data available always, right? I guess the only way to minimize both type 1 and type 2 error is having constant surveillance so that in the courtroom they can pull up all of the data ever and find out exactly what happened, and then there would be no mistakes, right? But that's a whole nother problem, right? So, you know, do we want to be able to collect all data at all times? You know, that's probably another whole another set of questions. So if we're in a system where we don't have all of the data available to us, we are at risk of committing a type 1 or type 2 error. And you have to decide which type of error is worse. So in this scenario, a type 1 error is worse than a type 2 error, okay? So in the criminal trial, if we decide that the type 1 error is worse, that it's worse to have a false positive, in this scenario, do we want a large alpha or a small alpha? Okay, so alpha is the risk of a type 1 error. So we would want a small alpha, right? So if the type 1 error is worse, okay, we would want to pick a small alpha. Right. And they say this in court. What do they say? What do they tell the jury? Beyond a reasonable doubt, right? They don't say use a small alpha, but they say you want to, you know, be sure beyond a reasonable doubt. Okay, meaning they don't want you to convict someone because you just have this gut feeling and you feel like the person is guilty. Okay, they don't want that. They don't want stuff like that. Okay, so they say beyond a reasonable doubt. Okay, but they don't say basically use alpha equal to 0, meaning you are absolutely certain. Okay, they don't say you want to be 100% with 100% certainty. Okay, because what would happen if we set alpha equal to 0? So let's say you have a judge who has this moral conundrum and says, you know, I never want to send an innocent person to jail. Okay, that's a reasonable conviction to have, or a reasonable feeling for a judge to have. Okay, what would happen if alpha equals 0, right? So the judge says, you know, I never want to send an innocent person to jail, okay? And so to be absolutely certain that the judge never sends an innocent person to jail, what would have to happen? The only way the judge can be absolutely certain that he or she never sends an innocent person to jail is if this judge acquits every single person, okay? Because as soon as the judge sends one person to jail without having 100% of all of the information, which is going to be every single situation, that person is at risk of having committed a type 1 error, okay? So if we set alpha equal to 0, we would never reject the null hypothesis. Okay, which means we will commit many, many type 2 errors. All right, and that judge would probably be removed quite quickly if the judge gains a reputation of never convicting anyone ever, right? Right. Even in cases where it feels very, very certain, if the judge says, well, I didn't know 100%, so I didn't want to convict the person or send the person to jail, then yeah, I think people would have a problem there, okay? And on the other hand, if a type 2 error is worse, than type 1, okay, we would pick a large alpha. Okay. We have control over the alpha we use. We don't really have control over beta. Beta is related to a bunch of things, okay? We have control over the alpha we use. Okay. We do not have direct control over beta. Flip the page. So beta is the probability of type 2 error. What would 1 minus beta be? Beta is the probability of type 2 error. So anytime you do 1 minus a probability, what do you get? You get the complement, right? So 1 minus beta would be the probability of not committing a type 2 error. Okay, which is not a type 1 error, okay? So think about the trial, okay? Type 1 error is sending sending an innocent person to jail, type 1 error. Type 2 is letting a guilty person go free, okay? Not doing that would be what? So not letting a guilty person go free, which means sending a guilty person to jail, okay? So probability of not committing a type 2 error, this is the probability of correctly rejecting the null when the null is false. Okay? And so 1 minus beta, this is called power, okay? We give it a special name. Power is the probability of correctly rejecting the null when the null is false. This is something we want, right? Okay. Bless you. All right, so let me give you a scenario where the type 2 error is worse, okay? So think of, I don't know, okay. So imagine like a HIV test, okay? All right. So generally, when you go in, they would assume, the doctors would assume that you don't have HIV unless your test comes back indicating that you might, okay? So the null hypothesis would be patient is free of HIV, and then alternative will be patient has HIV, okay? All right, what would, so in the ideal scenario, if someone does not have HIV, the test says negative, and then if someone does have HIV, the test says positive. Okay? All right. Type 1 and type 2 errors. What would a type 1 error be, and what would a type 2 error be?
What would be conditions free, but the test says that they have conditions?
Yeah, so type 1 error would be patient does not have HIV, but the test says the patient has the disease, okay? Test. And I mean, that's a bad situation. We don't want that, okay? Type 2, what would a type 2 error be, though, okay? Patient does have HIV, but the test says the patient does not have HIV, okay? All right, and so, you know, if we were forced to err on one side or the other, which error is worse than the other? The type 2 error is worse, right? This has significant epidemiological consequences, right? So the type 2 error is worse. Okay. And so in this case, we want all of the tests to be as sensitive as possible. Okay. If there's even a possibility that someone has HIV, we want the tests to indicate as such. Okay. And oftentimes, you know, you might go in for additional testing in case. Just to make sure that it wasn't a fluke after one test or something like that, okay? And the same with, you know, cancer screening. A lot of these health-related things, type 2 errors will be worse. So with cancer screening, your initial checkups and things like that, you know, you're supposed to do like if you're a woman, you're supposed to do breast self-exams every month, or if you're a guy, you're supposed to do testicular exams every month. And it's just, if anything is unusual, you're supposed to go see the doctor, okay? And it might turn out that there's nothing wrong with you, okay? But it's much better that you go check the doctor to make sure that you're healthy or not healthy, get a more thorough check than to ignore that and actually have cancer and think that you don't, or something like that, okay? And that's, and so anytime there's self-diagnostics involved, basically, these often go with type 2 error is worse, and so you have this very high alpha, okay? And that's why places like WebMD are, it's like any symptoms you look up, it says it could be cancer, right? And that's because, you know, it's probably not going to be cancer, but just in the off chance that it is, they want you to be aware and look into it further, because if it would be much worse that, you know, you go on WebMD and say, oh, well, I'm probably healthy, when in reality you have something wrong with you, okay? So, but again, you know, the flip side is if you have alpha set too high, then people kind of treat WebMD as almost like the boy who cried wolf, right? You know, they make memes and jokes about how WebMD always says it's cancer, but that's because type 2 error would be worse in that scenario. Okay. I'm thinking I'm going to just keep going in the lecture, and then we'll finish a little bit early today. Is that okay? Yeah. Is that good? All right. Somebody said yes, so. So we'll go with that. Huh? You're all thinking it? Okay. All right. Well, yeah, I don't want to make any promises about exactly what time we're going to end, okay? All right, okay, so let me just kind of do a quick review and recap of all of our, I don't know, statistical inference stuff. For the final exam, you're allowed to have a note sheet with writing on the front and back. I believe. Let me just check here. I believe I have put. What's going on? Oh, wrong. I believe I put formula sheets on. Practice final exam. Oh, okay. I have to update this. I have a study guide and I have a formula sheet. Okay, so there it says study guide, but this is more so it's a guide to inference is really the correct description here. Okay, and then there's a formula sheet, but I've got to upload that. Okay. All right. So anyway, well, as you approach problems in the practice final and on the final exam itself, the most important thing is to figure out what kind of problem you're dealing with. Okay. So you have we have confidence intervals for P. So proportions, we'll say one sample. Okay, and then we have confidence intervals for means, one sample. We have confidence interval for means, two samples. Okay, we also have hypothesis tests for proportions, one sample. Hypothesis tests for proportions, 2 samples. Hypothesis tests for means, 1 sample. And hypothesis test for means, 2 samples. Okay, so you're going to have to be able to identify which of these scenarios or circumstances you're dealing with, because if you mess up this part, then the rest of your problem will go badly. All right, so basically, to decide between proportions versus means, okay? Proportions versus means. Okay, if the data is categorical, you're dealing with proportions. Okay, so, you know, other keys that it will be proportions will be the data is given as a count of a certain category or a certain group. Given as, you know, something like 36 out of the sample are whatever, okay? Something like that, okay? Counts. Counts of, quote, successes. So those would be proportions. Also, obviously, if the test problem mentions the word proportions, then that'll be a good indication that you're dealing with proportions, okay? On the other hand, if the data is numeric, then you will be dealing with means. Okay? If in the problem it talks about the average whatever, okay? You know, you see words like the average or the mean, then you're dealing with means. Every problem with means requires a standard deviation, okay? A standard deviation is needed. So if you can't find a standard deviation anywhere in the problem, chances are it's not going to be a means problem, okay? Okay, a standard deviation is needed for these problems. Okay. And this sounds very, you know, basic, but every quarter, some students mess this up. Okay, so you don't want to mess these things up. All right, whether you have 1 sample or 2 samples, the best way to decide whether you have 1 sample or 2 samples is try to identify how many ends you can are in the problem, okay? Okay, how many ends can you find? N being the sample size. Okay, so when you're reading a problem, if you can only identify 1 sample size, 1 N, then it's going to be a 1 sample problem, okay? Okay, and then do you have confidence intervals or hypothesis tests? For confidence intervals, you're going to definitely see somewhere in there a confidence level, 90% confidence or 95% confidence level or something like that. You will definitely see a confidence level somewhere in the problem. Okay. And then for hypothesis tests, you will almost certainly see the word hypothesis, or certainly see the word test somewhere in the problem, okay? And I know it sounds silly, but I can't think of a hypothesis test problem where it doesn't say perform a test or something of mentioning hypotheses somewhere in there, okay? So either hypothesis or test or both will appear in the problem. Okay. Also, p-values are only for hypothesis tests, okay? P-values are for hypothesis tests only, okay? So if any of the problem mentions a p-value, then it's a hypothesis test, okay? Okay. All right, so I'll just start throwing some formulas up on the screen, kind of recapping everything together, and then I think that'll be that's pretty much it. Are there and of course, if there's any questions along the way, I'm happy to try to clear things up. Okay, so I'm going to cover confidence interval stuff. So we'll start with confidence intervals for P, one sample. So we never covered confidence intervals for P with two samples, okay? So we got confidence interval for P, one sample. We've got confidence interval for mu, one sample. And then we have confidence interval for mu1 minus mu2, two samples. Okay. You know what, let me, before I forget. I'll take attendance today, all right? Anyway, so just write your name, pass this around. Okay, so confidence intervals for P with one sample, it's going to be, the primary formula is, well, all of these, okay, all will be the center of the interval plus or minus critical value times standard error. Okay, and so in this case, we've got the center is P hat plus or minus Z star times the standard error, okay? The standard error is the square root of P hat times 1 minus P hat over N. Z star, there's 4 values, 1.28, 1.645, 1.96, 2.58. This is 80%, 90%, 95%, and 99%, okay? So again, here, center plus or minus the critical value times the standard error. Critical value times the standard error together, what's that called? Margin of error. Okay, so here you have, in the center you got x bar plus or minus t star times the standard error. The standard error, s over the square root of n. T star has degrees of freedom equal to n minus 1 I'm going way too fast here. I apologize. T star has n minus 1 degrees of freedom, and you look up in the T table. Center plus or minus critical value times the standard error. So in the center here we have x bar 1 minus x bar 2. Our critical value is T star. We have our standard error. The standard error is uglier formula, s1 squared over n1 plus s2 squared over n2. T star has degrees of freedom equal to n minus 1. Use the smaller of n1 and n2. And you look it up in the table. Okay, and so that's how we create our confidence interval. What are the correct interpretation of each of these is, for this one is I am, 95 whatever % confident, or 99 or 98, or I'm sorry, 90 or 80 or whatever, that, so for this first one we're, blank % confident that what is between the ends over the interval? That the population proportion P is, within the interval. Over here we'd say I am blank % confident that the population mean is within the interval. And this last one we would say I am blank % confident that the mean of population 1 is between blank and blank, more or less than the mean of population 2. So the last one you're talking about the difference between the two population means, whereas the other ones you're talking about the population mean directly. So when you have one sample, it's about the population mean directly. 2 samples, you're talking about the difference between the two population means. Okay. Are there any questions on this?
Can you just one more minute?
Yeah, I'll leave it up there. Is the attendance paper coming around?
Yeah.
Okay, okay. Just make sure you guys sign it before you leave. Okay, I'm gonna flip. Yes. Great. Okay. All right, and then so now we'll talk about hypothesis tests. Okay, so we'll do hypothesis tests for P, and then I'll do hypothesis tests for P1 and P2. So this is 2 samples over here, just 1 sample. Okay, so here the null hypothesis is P is equal to some number P0. So for example, the null hypothesis is that P is equal to 0.47 or something like that. Someone claims it's 47%, whatever it is that we're talking about. And then the alternative is P does not equal P0, okay? Or greater than or less than, okay? Depending on the question. Okay, the checking conditions will be kept separate from the rest of the problem. So all of the problems on the final exam, you can assume that the conditions are met, okay? Other than the one section where it says check the conditions, okay? And all the problems where you do calculations and stuff, you can assume that the conditions are met, okay? Because when I wrote them, I made sure the conditions are met. All right, so you're going to do standard error. We've got P0 times 1 minus P0 divided by n, okay? So, make sure you're using P0 when you're doing hypothesis test and you're doing P hat when you're doing a confidence interval, okay? Your test statistic here is going to be a z, and it's the difference between the reality versus the expectation, which is P hat minus P0, divided by the standard error, okay? And then you will look up z in the z table, okay? Whenever you're dealing with proportions, you'll always be using the z table. Okay, look up z in the z table, and then over here, the null hypothesis is P1 is equal to P2, or it can also be written as P1 minus P2 is equal to 0, okay? Okay, and then the alternative is either P1 does not equal P2, or is greater than, or is less than, okay? Or you've got not equal to 0, or greater than 0, or less than 0. Standard error, oh, before we do the standard error, we need to find overall P hat, which is going to be x1 plus x2 over n1 plus n2. Your standard error is the overall P hat times 1 minus P hat times 1 over n1 plus 1 over n2. Your test statistic z is going to be P hat 1 minus P hat 2 over the standard error. Okay. And again, you'll look this up. Look up z in the z table. Right. And then whether you use the left side or right side, that all depends on, if the alternative has a less than sign, p-value is area to the left of z. If the alternative has a greater than sign, then the p-value is area to the right of z. Okay? And if the alternative has a not equal, then the p-value is 2 times the tail area. Sometimes students ask, how do I remember what's the tail area? Basically, just take your tail area, whatever you find in the z-table, and multiply it by 2, okay? If you get an answer that's bigger than 1, you did it wrong, okay? So if you're getting the answer bigger than 1, then you have to take that and subtract it from 1 first to get your tail area, and then you multiply it by 2, okay? Because the p-value is a probability, meaning you should never have a probability bigger than 1. Okay? So if you ever get a probability bigger than 1, you did something wrong. All right, so that's hypothesis testing stuff for proportions, and then all we have left is hypothesis testing stuff for means. Flip the page here. Okay, so over here, the null hypothesis is that mu is equal to some number, mu 0. So for example, the null hypothesis could be that mu is equal to 142. And then the alternative will be mu does not equal mu 0. Or, mu does not equal 142. Or that mu is greater than mu 0 or is less than mu 0, okay? However you want it. All right, the standard error, S over the square root of n. Your test statistic t, x bar minus mu 0 divided by the standard error. Okay, and then you'll look up t in the t table. Degrees of freedom is equal to n minus 1. Over here, your null hypothesis is that mu1 and mu2 are equal. Alternatively, it could be written as mu1 minus mu2, that the difference between them is 0. That's totally fine. And then the alternative will be mu1 is not equal to mu2, or it could be written as mu1 minus mu2 is not equal to 0, or is greater than 0, or is less than 0, okay? Or standard error in this case s1 squared over n1 plus s2 squared over n2. And then your test statistic t is the difference between your sample means, x bar 1 minus x bar 2, divided by the standard error. Again, we're going to look this up. Look up t in the t table. Degrees of freedom is equal to n minus 1. Okay, and then the way you do is, find the columns that t is between. Between, or or to the left of, or to the right of, and look at the column headings to get your tail area. Okay, so if the alternative has a greater than sign, then the p-value is equal to the right tail area. If the alternative has a less than sign, then your t will most likely be negative, or should be negative. then basically pretend all the numbers have negative signs, and then you've got the left tail area, okay? All numbers in the table are negative. And then the p-value is equal to the left tail area. And then if the alternative has a not equal sign, then the p-value is 2 times the tail area. All right. Is that good? Okay. Any questions? All right, we'll end a little early today then. Your homework this week is to go through the practice final. If you haven't signed the attendance sheet, please make sure you do.
Do you have a quiz next week?
Yes, we do. Okay. Just covering the stuff that we covered today.